Welcome back to the Deep Dive. Today, we're attempting to wrestle with a mind so powerful, so diverse in its interests.
I mean, where do you even begin with someone like that?
Exactly. Cataloging his achievements feels like trying to map an entire galaxy. And funnily enough, this is a scientist who has actually mapped a good chunk of the cosmos.
He really has.
We're talking, of course, about Sir Roger Penrose, the English mathematician born in 1931, whose career is it's this sprawling epic.
It absolutely is. And that's our mission today, really. We're trying to unpack the work of a genuine polymath who seems to operate on several different planes of reality at the same time.
That's a great way to put it.
You have the foundational, the irrefutable physics that earned him half a Nobel Prize. That's a legacy built on absolute mathematical rigor.
Right.
But then, on the other side of his work, you get these highly philosophical and, let's be honest, deeply controversial theories.
Very controversial.
Ideas on cyclical cosmology and human consciousness, specifically his arguments against what we call strong artificial intelligence.
And that's the core hook, isn't it? That central tension that defines his legacy and why we have to dig into all the source material we've gathered.
Absolutely.
On one hand, you have a Nobel laureate, someone recognized for proving with mathematical certainty that black holes are an inevitable prediction of general relativity. This is solid, set-in-stone physics.
Right.
And yet, he's perhaps equally famous for arguing, often against the entire scientific community, that the human mind simply cannot be reduced to a computer algorithm.
Because consciousness, in his view, requires a physics that we don't have yet.
It's this dichotomy of certainty and speculation.
Uh-huh.
And we need to tackle both sides of that coin with equal seriousness.
Okay, so let's start with that concrete foundation. The Nobel-winning physics. Penrose was awarded half of the 2020 Nobel Prize in physics.
And I think it's really important to get specific here. The recognition wasn't just for, having a general idea about black holes.
No, not at all. People had been conceptualizing them since the 18th century, really. This was for providing the rigorous mathematical proof.
Showing, and this is the key phrase, that black hole formation is a robust prediction of the general theory of relativity.
Exactly. It meant they weren't just mathematical oddities that might happen under perfect conditions. They were necessary. They had to form.
And the context of that prize is key, too. He shared it with Reinhard Genzel and Andrea Ghez.
Right, who did the observational work.
Decades of it. Using precise methods to confirm the existence of Sagittarius star, the supermassive compact object at the center of our own galaxy.
So the prize itself perfectly married theory and observation. You have Penrose with the unshakable theoretical framework.
And then Genzel and Ghez providing the astronomical evidence that, yep, it's really there.
Now, the initial theoretical breakthrough came way back with his seminal paper in 1964. And the physicist Kip Thorne, who you definitely know, he noted that Penrose, in that single paper, revolutionized the mathematical tools used to analyze spacetime.
Before him, what was the state of the field?
Well, before Penrose, most of the work on the curved geometry described by Einstein's equations was confined to highly symmetrical situations.
So like a perfectly spherical, non-rotating star collapsing.
Exactly, the Schwarzschild solution. But the real universe isn't that clean. What if the star wasn't perfectly spherical, or the collapse wasn't symmetrical?
The math gets impossible.
It becomes so complex that physicists weren't sure if singularities would actually form, or if the messiness of it all would just let the star bounce back or something.
So the big challenge was finding a way to analyze a messy, real-world gravitational collapse without having to solve Einstein's full, nightmarish equations for every single case.
Right. And his strategy for getting around that was, well, it was ingenious.
What did he do?
He fundamentally shifted the focus. Instead of trying to define the specific detailed metric, the exact geometry of spacetime, which was just too hard to solve, he concentrated on the topology of the space.
Okay.
And crucially, the conformal structure of space.
All right, we have to unpack conformal right away. What does that mean in this context, and why was that so powerful?
Think of it like this. The conformal structure is basically the layout of the light cones.
And a light cone is just all the possible paths light can take from a single point in spacetime.
Precisely. And since nothing can travel faster than light, those light cones define causality. They tell you what can influence what.
Okay, got it.
Now, when we say conformal, we mean a structure that preserves angles but not necessarily distances. It lets you stretch or squeeze the overall map without changing the fundamental causal structure, which is all in the angles of those light cones.
So by focusing on the light cones, he's really just focusing on the cause and effect relationships, Why does that get around the hard math?
Because Penrose realized that even in a chaotic, messy, asymmetrical collapse, the structure of those light cones, the causal structure, has to behave in a certain way once gravity gets strong enough.
Ah, so he found a general rule that applies no matter what the specifics are.
Exactly. He proved that once the mass is concentrated beyond a critical point, the causal paths get so warped that they have to terminate at some kind of boundary. It doesn't matter what the star's initial shape was or if it was spinning, the collapse becomes unavoidable.
And that rigor is what led directly to his huge 1965 paper, the one with the Penrose singularity theorem.
That's the one.
And the absolute non-negotiable conclusion of that paper was what?
The conclusion was that if any object, like a dying star, implodes beyond a certain point, the gravitational field inevitably becomes so strong that it must form some kind of singularity.
So the geometry of spacetime just can't handle it otherwise.
It can't. The collapse is unavoidable. So it stopped being a theoretical quirk that depended on perfect symmetry and became a necessary outcome of general relativity in the real world.
And as the source material points out, this new way of thinking wasn't just limited to collapsing stars.
No, not at all. It provided a whole new framework for thinking about singularities in general. And this is what set the stage for his famous collaboration with Stephen Hawking.
Right. Hawking then took Penrose's techniques and applied them to the entire universe.
He did, which led to the Penrose-Hawking singularity theorems. They basically generalized the concept, showing that singularities weren't just a feature of black holes, but that space-time itself must have had a beginning.
The Big Bang, a singularity in our past.
And they shared the 1988 Wolf Prize for that foundational work.
So, okay, once you've established that singularities are a necessary evil, the next logical question is, how does the universe deal with them? These points of infinite density and gravity.
And that moves us straight into his ideas on black hole mechanics and one of his most influential and still unproven hypotheses.
The cosmic censorship conjecture.
Formulated in 1969.
I love the name. It sounds like the universe is trying to hide something indecent from us. What's the core idea of this censorship?
It's pretty much that. The conjecture suggests that any singularity that forms must always be confined within a well-behaved event horizon.
Which is the boundary we call the black hole, the point of no return.
Right, so the singularity itself is hidden from the outside world. If the conjecture is true, then this dangerous region where general relativity breaks down is always cloaked, which keeps the rest of space-time orderly and predictable.
Because the alternative would be a naked singularity.
A point of infinite gravity that's just out there, visible to any outside observer. And if those existed, they could mess with predictability across the entire cosmos, because the laws of physics will be breaking down right where we could see them.
That sounds like a complete nightmare for physics. If GR breaks down in a visible spot, then anything could happen. Determinism goes out the window.
It's a huge problem. And Penrose actually proposed two versions of this. There's the weak cosmic censorship conjecture, which is what we just discussed. Singularities from gravitational collapse are hidden from us far away.
But then he formulated a stronger one.
Yes, the strong cosmic censorship hypothesis, or SCCC, in 1979.
How does the strong version differ?
The strong version is much more restrictive. It argues that space-time itself is fundamentally deterministic. It basically states that any reasonable spacetime has to be free of naked singularities everywhere, even locally. The cosmic sensors are always at work.
And settling this is still a huge open question in physics.
One of the most important, outstanding problems in general relativity. It's an active debate that really gets at the fundamental predictability of our universe.
So beyond just hiding the singularity, Penrose also figured out a way to extract energy from a black hole, which just sounds completely counterintuitive.
It does, doesn't it? How do you take energy from the ultimate trap?
This is the Penrose process.
And it's just a beautiful piece of physics. The trick is you're not taking the energy from inside the event horizon. You're getting it from a region just outside called the ergosphere.
And what's special about the ergosphere?
The ergosphere only exists around rotating black holes because the rotation literally drags space-time around with it, a phenomenon called frame dragging. In the ergosphere, that frame dragging is so intense that nothing can stay still relative to a distant observer. You are forced to move with the black hole's rotation.
But you can still escape, unlike from the event horizon.
Critically, yes.
Yeah.
You can still get out. So here's how the Penrose process works. An incoming particle enters the ergosphere and splits into two.
Okay.
One of those new particles falls into the black hole. But here's the genius part. That infalling particle can have negative energy as measured by someone far away.
How is that even possible?
The intense frame dragging warps the energy equations. So when this negative energy particle falls in, the other particle, the one that escapes, has to conserve the total energy. So it flies out with more energy than the original particle had to begin with.
Wow. So you're basically tapping into the black hole's rotational energy.
You are literally converting the black hole's spin into the kinetic energy of the escaping particle.
That's incredible. It's almost like a cosmic slingshot. And is this thought to have any real-world applications?
Oh, yes. It's theorized that the Penrose process could be responsible for some of the extreme power outputs we see in things like quasars, the colossal energy they emit as matter gets processed by these supermassive spinning black holes.
It's a mechanism for energy extraction, not creation.
Precisely.
Okay, one last thing before we move on from this part. We have to talk about the visual language he created, because physicists use it every single day.
You have to mention Penrose diagrams.
They're absolutely everywhere in
Wow.
relativity and cosmology.
They are. Penrose diagrams, or causal diagrams, are these essential tools for visualizing space-time geometry. And the key is that they map the entire infinite extent of space-time, all of space and all of time, onto a finite diagram.
Which usually looks like a diamond or a square on a piece of paper.
Right.
But how do you do that? How do you map infinity onto a finite space?
He used a technique called conformal compactification, which brings us right back to that conformal structure we talked about.
With the light cones.
Exactly. By scaling down the metric in a very specific way, you preserve the angles, the causal relationships, but you squeeze infinite distances down into a manageable size.
So physicists can just draw out things like the event horizon, the singularity, even future and past infinity, all on one piece of paper.
It's the standard blueprint for discussing relativistic dynamics. His architectural impact goes right down to the very language physicists use to talk to each other.
It's so clear that his contributions to gravity and cosmology are just monumental. I mean, Nobel-worthy.
Absolutely.
But what I think really makes him a polymath is his simultaneous mastery of pure geometry and his influence on art and math completely outside of astrophysics.
Yes, this is the geometric bridge in his career, and it gives you a completely binding view of his mind.
To really get it, you should probably look at his background. He was clearly immersed in this kind of thinking from a very young age.
Oh, definitely. He came from a family of high achievers, all specializing in pattern recognition and analytical thought. His father was a distinguished psychiatrist and geneticist.
He had a brother who was a physicist, another who was a chess grandmaster.
And his stepfather was Max Newman, the mathematician and computer scientist who was central to early computing. So mathematical rigor wasn't just a career for him, it was, the family trade.
He got his PhD in algebraic geometry in 1957. And even as a student, he was already making waves in pure math, completely unrelated to black holes.
Totally. The sources point out that in 1955, while he was still a student, he independently reinvented something called the E.H. Moore generalized matrix inverse.
Which is now known as the Moore-Penrose inverse.
Universally.
So why is a generalized inverse important? What does it do?
Well, most of us learn about the standard matrix inverse, which only works if a matrix is square and non-singular.
Right.
But in so many fields, statistics, engineering, data analysis, you need to sort of invert rectangular matrices or singular ones to solve systems of equations. The Moore-Penrose inverse gives you a unique, standard way to do that.
And the fact that he came up with it on his own says a lot about his intuition.
It says volumes. It shows he could see the need for a mathematical tool before it was even widely used in his own field.
But I think the most delightful intersection of math, art, and just pure curiosity came in the 1950s with those impossible figures.
This is where we get the iconic Penrose triangle, or the tribar. He devised it with his father.
It's an object that looks perfectly fine in a two-dimensional drawing, but is completely impossible to build in three-dimensional space.
He called it impossibility in its purest form.
And the genius of it is how it just completely tricks your mind. It's a closed loop that looks like it's continuously going up on all three sides, but it brings you right back where you started.
Your visual system processes the local edges just fine, but when you try to put it all together globally, it's a paradox you can't resolve.
And the fame of the triangle is maybe even secondary to the amazing creative loop it sparked with the Dutch artist M.C. Escher.
Oh, that anecdote is fantastic.
So how did Penrose's math end up inspiring Escher's art?
Well, it actually started with the inspiration flowing to Penrose. As a student in 1954, he saw an Escher exhibition in Amsterdam and was just mesmerized.
Yeah.
That inspired him and his father to create their own impossible figures like the tribar and the endless staircase. They published an article, sent a copy to Escher.
And Escher was blown away.
Profoundly affected. He explicitly said he used their geometrical ideas to produce two of his most iconic masterpieces, Waterfall and Ascending and Descending.
So, just to get this straight, Penrose sees Escher, which inspires him to create impossible geometry, and then Escher takes that geometry and turns it back into world-famous art.
It's a perfect feedback loop of influence. It just shows that Penrose wasn't only a physicist, he was a geometric conceptualist whose ideas resonated far outside of academia.
And this blend of pattern and impossibility really hit its scientific peak in 1974 with the discovery of Penrose tilings.
This is a truly remarkable achievement in pure geometry, and it had completely unexpected consequences for physical science.
So Penrose tilings are these non-periodic tilings that use a very small set of shapes. In the simplest case, just two tiles.
Right, often called the kite and the dart.
Okay, what does it mean to tile a plane non-periodically?
A standard tiling, like a checkerboard or a bathroom floor, is periodic. If you slide the pattern over, it matches up perfectly with itself.
It repeats.
Penrose tilings never repeat, no matter how far you extend them. They have local matching rules that make them fit, but those same rules prevent any global repeating pattern from ever forming. And what makes them so special is that they exhibit fivefold rotational symmetry.
And back in the early 70s, fivefold symmetry was considered a big deal, right?
A huge deal. For centuries, crystallographers believed it was impossible in traditional periodic crystals. If you try to stack atoms in a perfectly repeating 3D lattice, you can only get 2, 3, 4, or 6-fold symmetry, never 5.
So Penrose's tilings with this forbidden symmetry were just a beautiful mathematical curiosity at the time.
Purely abstract geometry, until they weren't.
Because within a decade, this abstract math connected directly to physical reality.
Yes. In 1984, the materials scientist Dan Shechtman discovered materials whose atomic arrangements showed this exact fivefold symmetry.
He called them quasicrystals.
And they physically materialized the non-periodic order that Penrose's abstract tilings had predicted. It was this amazing moment where Penrose's geometric insight actually predicted a new state of matter that was thought to be impossible.
Shechtman later won the Nobel for the discovery.
He did, but the foundational mathematical structure came directly from Penrose's work. It's such a powerful statement on the utility of pure math.
And beyond these more popular geometric puzzles, he also invented some incredibly profound theoretical tools that are now fundamental to modern physics research. Let's touch on two: twistor theory and spin networks.
Okay, twistor theory, which he came up with in 1967, it's probably the most difficult theory he ever proposed.
And that's saying something.
It is. It's a highly complex mathematical approach to reformulating physics. The idea is to map geometric objects from our normal space-time Minkowski space into a four-dimensional complex space, which he called twistor space.
Why? Why move physics into this super abstract space? What's the point?
The goal was unification and simplification. In twistor space, many really complex differential equations like Maxwell's equations for light become purely algebraic.
So it simplifies the math.
Immensely. Penrose hoped it might provide a more fundamentally geometric description of nature and maybe even get around some of the nasty infinities that plague quantum field theory.
And has it become a fully unified theory?
Not yet, but it's proven to be incredibly productive in certain areas of mathematical physics. It's another example of his tireless search for the deeper mathematical structures that he believes underlie physical laws.
And then there are spin networks.
Invented in 1971, these are basically graphical ways to describe the quantum state of a volume of space. Imagine drawing a network of lines and vertices. The lines represent fundamental bits of area, and the vertices represent units of volume. These networks later became the foundational geometry of space-time in a theory called loop quantum gravity.
So in loop quantum gravity, space-time itself isn't a smooth, continuous fabric. It's made of discrete, quantized loops and nodes.
Precisely. The geometry is granular, the area of a surface is quantized, and it's measured by the spin values on the lines of the network that pierce through it.
So Penrose literally provided the mathematical scaffolding for one of the main competitors to string theory.
He did. Another demonstration that whether he was working in pure geometry, general relativity, or the quantum description of gravity, Penrose was always there providing the essential foundational mathematical architecture.
All right, now we have to enter the realm of deep speculation. We're moving from his proven, Nobel-cemented work into his theories on the origin of the universe and the fate of time.
Yes, specifically his concept of infinite cycles. This is where he really starts to challenge the established paradigm.
The foundational problem he's trying to solve here is one of the biggest puzzles in cosmology, right? The asymmetry of time.
The second law of thermodynamics, exactly. Why did the universe start in such a ridiculously low entropy, highly ordered state at the Big Bang?
All the other laws of physics are time reversible. But the second law says entropy always increases. So where did that initial smoothness come from?
It's the past hypothesis problem. The Big Bang should have been chaotic and high entropy, but when we look at the cosmic microwave background, it's incredibly uniform.
So Penrose tried to explain this with something called the Weyl curvature hypothesis, or WCH, back in 1979.
Right. He argued that the initial conditions of the universe, near the Big Bang singularity, had to have a specific geometrical property to explain the area of time.
What exactly is Weyl curvature, and what does the hypothesis say?
So Weyl curvature is the part of the gravitational field that represents tidal forces, the stretching and squeezing of space-time, but not density itself.
It's what makes the field of a black hole lumpy and dynamical, as opposed to the smooth field of the sun.
A great way to think about it. And the WCH basically says that the Weyl curvature must have been zero at the Big Bang singularity, but it can be unrestricted at the final end state of the universe.
And zero Weyl curvature means the geometry of the early universe was
Perfectly smooth, conformally flat, free of tidal gravitational forces. It was highly ordered, very low entropy.
And as the universe evolves, gravity causes stuff to clump together, forming galaxies and stars and black holes.
And that process generates tidal forces, which means the Weyl curvature grows, and so does entropy. So the WCH gives a geometrical reason for why the Big Bang was so smooth and set the clock for the thermodynamic arrow of time.
And this Weyl curvature hypothesis is the mathematical bedrock for his most controversial cosmological theory, Conformal Cyclic Cosmology, or CCC.
Which he laid out in his 2010 book, Cycles of Time.
And the core idea of CCC is it's audacious.
It's that the universe doesn't have a single beginning and end. Instead, it goes through infinite sequential cycles, which he calls eons. The future of one eon seamlessly becomes the past of the next.
Okay, so let's walk through the mechanism of one of these eons. Where does it start, and how does it transition?
It starts at the Big Bang, and then it expands and cools for an unimaginably long time. Eventually, it reaches a state of being incredibly vast and cold. Crucially, Penrose suggests that at the end of this eon, all matter, even protons, will have decayed, and the only things left are black holes.
Which then evaporate through Hawking radiation.
Exactly. So at the ultimate, far future endpoint, the entire universe is made up of nothing but massless particles, mostly photons.
Okay, that cold, empty, photon-dominated universe sounds like a possible end state in standard cosmology. But the CCC twist is how this end state of infinite scale suddenly becomes a Big Bang again.
This is the critical, mind-bending part. Penrose argues that photons are massless, and because they travel at the speed of light, they don't experience time or space.
So the concept of scale, whether the universe is infinitely large or infinitely small, becomes physically meaningless from a photon's point of view.
Exactly. You're saying the Big Bang wasn't a dense, hot point of matter starting from nothing, but was actually the geometric continuation of an empty, cold, infinite universe.
That's precisely what the conformal structure lets him argue. Since only photons are left, and the WCH ensures the final state is geometrically smooth, the entire infinite space of the dying eon becomes conformally equivalent to a single point.
Which acts as the Big Bang singularity for the next eon.
So by doing a mathematical transformation, a conformal rescaling, the infinitely stretched out spacetime of the last eon gets compressed into the initial state of the new one,
seamlessly connecting them.
If that transition is purely geometric, that has huge implications for what the Big Bang actually is.
It does. Penrose argues that this means the mathematical singularity at the Big Bang is only an apparent singularity. It's a feature of our coordinates, not a physical end to reality.
Kind of like the event horizon of a black hole, which is also an apparent singularity you can get rid of by changing your coordinate system.
That's the analogy. Penrose suggests a similar coordinate change could remove the Big Bang singularity. And this leads him to argue that the physics near the Big Bang might not even need a full theory of quantum gravity.
Wait, he thinks we could use classical equations to describe the transition between eons?
He does, because the scale factor, the size of the universe, isn't physically relevant in that transition.
That feels like cheating. It sidesteps the need to unify general relativity and quantum mechanics, which is like the biggest problem in physics.
It's definitely a radical proposal. And that's why CCC is met with so much skepticism. It challenges the standard inflationary model and the whole idea of a single creation event.
Now, despite how speculative this all is, Penrose did claim to have found possible observational evidence for it.
He did, and it triggered a massive debate. In 2010, he and his collaborators claimed they found evidence in data from the WMAP satellite, which mapped the cosmic microwave background.
They said they found concentric circles in the CMB sky data.
Right. And they interpreted these circles as the imprints of violent events from the previous eon.
How would that work?
They hypothesized that powerful gravitational waves from, say, two supermassive black holes merging in the previous universe would pass through the transition zone and leave a circle of lower temperature variance in our own CMB.
So, ghostly echoes of the last universe.
It's a stunning claim, but the cosmological community was very quick to push back.
Why were the claims mostly dismissed?
The main criticism was about statistical significance. Other cosmologists argued that finding circles like that wasn't statistically surprising, given all the natural random fluctuations you'd expect to see in the CMB.
So you can find patterns in anything if you look hard enough.
That was the argument, that the methodology they used exaggerated the significance of these features. So while the idea is beautiful and the math is rigorous, the experimental proof is, well, highly questionable in the eyes of most physicists.
It just reinforces that Penrose is willing to follow his mathematical insights wherever they lead, even if the evidence isn't quite there yet.
So, if CCC tackles the universe's beginning and end, Penrose's other great speculative project tackles, maybe the most fundamental question of all,
The nature of human consciousness.
which he laid out most famously in his 1989 book, The Emperor's New Mind.
And this is just a direct frontal assault on the idea of strong AI.
Yes, the philosophical position that human thought, true understanding, intuition, sentience can all be replicated by a sufficiently complex computer running the right algorithms.
And Penrose's central argument is just bold and simple. The known laws of physics are inadequate to explain the phenomena of consciousness.
That is an immense claim. So if our current physics isn't enough, and classical computers can't do it, what does he think is required?
He suggests that human consciousness involves a process that is deterministic, but, and this is the absolute key, it's non-algorithmic.
And if it's non-algorithmic, it can't be modeled by a standard computer.
Right. He argues that to understand it, we'll need what he calls a correct quantum gravity, a new physics we don't have yet, to bridge the gap between classical physics, quantum mechanics, and brain biology.
So let's establish this core opposition. He's arguing against the view that all rational mental processes are just complex algorithms, and this philosophical argument is often called the Penrose-Lucas argument.
And it draws heavily on some foundational math from the early 20th century.
Absolutely correct. He uses variants of both Turing's halting theorem and Gödel's incompleteness theorem to argue that consciousness goes beyond formal logic and computation.
So Gödel's theorem basically says that in any formal system, there are true statements that you can't prove within that system. How does Penrose connect that to the human mind?
He argues that human consciousness, specifically our capacity for mathematical insight, allows us to see the truth of those Gödel statements.
Things that an algorithmic system, which is stuck operating by its fixed set of rules, could never prove on its own.
Precisely. So if the human mind can grasp truths that an algorithm cannot, then the human mind itself cannot be purely algorithmic.
It's a compelling argument.
Yeah.
But let's dig into the version he uses that's based on Turing's work. How does he explain something being deterministic but non-algorithmic?
He uses a variation of Turing's halting problem. The original problem asks if there's an algorithm that can tell you if any given program will eventually stop or just run forever.
And Turing proved no such general algorithm can exist.
Right. So Penrose imagines a simple physical system with two final states. Let's call them state A and state B.
Okay.
The system ends up in state A if a certain Turing machine halts, and it ends up in state B if it doesn't halt. So the system's final physical state is completely determined by the machine's outcome. It's deterministic.
But because of Turing's proof, there's no way to calculate that outcome in advance.
Exactly. There's no finite algorithm that can predict if it'll end in state A or state B. Penrose argues that human consciousness, especially our ability to have those aha moments of insight, must involve some kind of non-algorithmic physical process.
So he's saying reality itself at some deep level might be non-computable.
That's the implication.
So he identifies this gap in known physics, but he doesn't just leave it there. He proposes a very specific biological mechanism for where this could be happening.
Yes, in collaboration with the anesthesiologist Stuart Hameroff. This is the famous, or maybe infamous, orchestrated objective reduction theory.
Or.
Right. They postulated that consciousness comes from quantum gravity effects happening inside these tiny structures within brain cells called microtubules.
What are microtubules, and why do they focus on them?
Microtubules are protein polymers. They're these cylindrical structures that make up the cytoskeleton of our cells, including neurons. They provide structural support, act as little transport highways inside the cell.
And Hameroff noticed their highly regular repeating lattice structure.
And he theorized they could sustain and process quantum coherence because of that ordered structure. They suggested the whole system was complex enough to let a quantum superposition exist across many neurons at once.
And what does the objective reduction part mean?
Well, the standard Copenhagen interpretation of quantum mechanics says the wave function collapses, the reduction, when it's observed or measured.
Right.
Orch-OR says the collapse isn't random or based on observation, it's objective. It happens when a specific threshold of space-time curvature related to quantum gravity is reached. And that process, happening in orchestrated cycles within the microtubules, is what generates a moment of conscious experience.
It's a unique theory, for sure, blending relativity, quantum physics, biology, but it's very much a minority view.
Oh, it met with enormous resistance.
What are the main criticisms leveled against Orch-OR?
The critiques are incredibly strong, and they come from computational neuroscientists and physicists. Marvin Minsky, one of the fathers of AI, was probably the most vocal critic from the computational side.
And what was his argument?
Minsky basically argued that Penrose was wrongly looking for new principles of physics when he should have been focused on the immense complexity of the brain as a machine that can be explained by current science.
So Minsky's view was that humans are machines, just extremely complicated ones, and we don't need to invoke some exotic new physics.
Exactly. Just better computational models.
So that's a debate about methodology. But there was also a very specific physics challenge to whether this could even happen in the warm, wet environment of the brain.
That came from the physicist Max Tegmark. He published a very famous paper calculating the timescale of quantum decoherence in microtubules.
And decoherence is the process where a fragile quantum state gets destroyed by its environment, the heat, the water molecules bumping into it.
All of it. And what Tegmark's calculations showed was that the timescale for decoherence in the brain's microtubules is incredibly short.
How short?
The quantum states would be destroyed in about 10 to the minus 13 seconds. He concluded that this is at least 10 billion times faster than what would be necessary for any kind of quantum consciousness effects to happen.
So in other words, the brain is just too hot and too wet for any kind of quantum computing to last long enough to be consciousness. The heat kills the quantum effect almost instantly.
That's the definitive challenge. Tegmark's work is often cited as the primary physical reason the Orch-OR theory isn't feasible. It puts a huge burden on Penrose and Hameroff to explain how microtubules could possibly avoid this.
But they haven't backed down. They've responded to the criticisms.
They've absolutely defended their theory. In 2014, they pointed to new experimental work from a scientist named Anirban Bandyopadhyay, who claimed to have observed quantum vibrations in microtubules in his lab.
So they saw that as potential support that quantum effects could be stable in these structures.
They did. And they published a big, updated version of the Orch-OR theory in Physics of Life reviews that year, sparking a whole new round of debate.
So regardless of where you land on the debate, his views on the non-algorithmic nature of human thought, they remain a minority view, but it's just a powerful testament to a brilliant mind applying mathematical rigor to a problem so foundational that it challenges the entire paradigm of reductionist science.
And when you step back and look at his whole career, you just realize the sheer scale of Sir Roger Penrose's impact.
The number of awards and honors he's accumulated really underscores his reach across so many different fields.
It does. Mathematics, physics, philosophy.
Let's just run through some of the major highlights just to really appreciate that scope.
His career was just marked by continuous recognition. The Adams Prize in 1966, the Heinemann Prize in 71. He was elected a Fellow of the Royal Society in 72. And then, crucially, he and Stephen Hawking shared the Wolf Prize in Physics in 1988.
For the Penrose-Hawking singularity theorems. That really cemented the importance of their early work together.
Absolutely. Then he got the Dirac Medal in 1989, the Albert Einstein Medal in 1990. So the gravitational physics community recognized his structural contributions long before the Nobel Prize.
And he also received high honors from the Crown.
He was knighted in 1994 for services to science, and in 2000 he was appointed a member of the Order of Merit, which is a very prestigious personal honor from the reigning monarch.
Then the Copley Medal in 2008, and of course the big one, the Nobel Prize in Physics in 2020 for the black hole work.
It's just an incredible list. The awards acknowledge everything from general relativity to his work on geometry and tilings and quasicrystals.
He really is the definition of a polymath, honored by multiple disciplines.
Bridging the pure abstract with the observational and the theoretical.
And beyond all the academic prizes, Penrose has also played a huge role in popularizing these incredibly dense and abstract topics for the general public.
That's a massive part of his legacy. The Emperor's New Mind from 1989, despite its controversial arguments, was a huge crossover success. It won the Royal Society Science Books Prize.
It introduced millions of people to concepts like Gödel's theorem and quantum mechanics.
Then he followed that up with the monumental The Road to Reality in 2004.
And that wasn't a quick read. It was billed as a complete guide to the laws of the universe. And it was, 1,099 pages?
That book alone is a lifetime of commitment to teaching. It covers everything from complex numbers to black holes to string theory. He really dedicated himself to explaining these complex ideas to the widest possible audience, always with an emphasis on the mathematical beauty that he sees underpinning reality.
So we've taken this incredible journey through the source material. We've gone from the mathematical certainty of black hole proofs
And the non-periodic certainty of the Penrose tiling.
all the way to the radical uncertainty of the Big Bang's nature and the possibility of quantum consciousness.
I think Penrose's career is just defined by his willingness to apply rigorous mathematical tools to tackle the most fundamental and often the most uncomfortable questions in physics and philosophy.
Whether or not the scientific consensus was with him.
Exactly. His two major legacies exist in this perfect complementary tension. On one side, you have the foundational, proven work, the mathematical architecture of black holes that won him the Nobel.
And on the other, the speculative and largely rejected theories, Conformal Cyclic Cosmology and the Orch-OR theory of consciousness.
It really raises a powerful final question for you to think about as you process all this. If a scientist contributes a proven foundational bedrock for future study, how should we value their deeply speculative yet innovative theories that challenge the status quo, even if those theories remain unproven or face sharp criticism?
Penrose consistently argued that mathematical insight, which he claims is non-algorithmic, should be what guides physics toward the edges of the measurable universe. So we're left asking, is that willingness to speculate, to challenge the prevailing paradigm, as essential to scientific progress as the proven foundational theorems themselves?